screen so that you can always see how pretty I look today. Except for it's not my good side. We've already discussed that. This is my good side, and you guys got to see my bad side. But I don't really have any bad sides, you guys. They're all good sides. So we're talking about exponents, right? And that's, you see it all the time. You see things written like with a little number at the top. It says, in the case of repeated multiplication with the same number, we can rewrite the expression using exponents. For example, here I have 2 times 2 times 2. So there's 3 of them. So I could write that as 2 to the 3rd power. The parts of an exponential equation are, I feel like the arrow should be lower here. It should be pointing more at the x, but we've got the base, right, which is the bottom part, right? In this case, 2 would be the base, and n would be the exponent, the power that we're raising it to, right? And all that power means is, well, how many times are we multiplying this thing, right? So we have 2 times 2 times 2, and it means we're multiplying it 3 times. So if I come down here and we start looking at these samples, I should probably write this as x to the power of n, or x to the nth power, right? Because we've got x and it's raised to the power of n. So if we look at the 2, we would have 2 to the 3rd power, right? Here I have 6 times 6 times 6 times 6 times 6. So our base is 6, and we're multiplying it 1, 2, 3, 4, 5 times. So it would be 6 to the 5th power. How would I know the value of that? I would plug it into a calculator. The cool thing about exponents is it's a good way to write really, really big numbers in a small thing, right? It's like saying 6 times 6 times 6 times 6 times 6. And if you'll notice on calculators all the time, sometimes you have like a little up arrow. Some of them will give you an exponent. Let's look at a calculator. Let's bring up a calculator. Yes, Jason. It says 6x to the nth power, right? Because we're raising x to the power of n, right? So we would read it as x to the nth power. If we did it like for the one we just wrote, this problem, it would be 6 to the 5th power. You're welcome. So how would we do this in a calculator? Well, let's open a calculator and find out. Right? Let's do a scientific calculator so that we can so we can find ourselves a scientific calculator and do it that way. So it wants the value of 6 to the 5th power. Now, sometimes you're going to see problems like this, right? Well, this says a squared or a to the b, right? That means we don't know. Like a squared, if it's 2, we could just use this and we could go, okay, well, that's going to give us a square, right? Like I could go 6 squared, but we don't want 6 to the square, right? We want 6 to the 5th power. So we're going to hit a to the b power, and then we're just going to put in 5. And it's going to give us that value, 7,776. Are all calculators going to be like this? No, right? I put in the Desmos scientific calculator online, but a regular calculator, let's put in a calculator. Yes, Caitlin. Yes, Caitlin? You have your hand raised? Yeah, the notes are posted, Jackson. Did you change your mind about a question, Caitlin? Oh, your mic's not working? You want to type it out? I was trying to figure out how they do exponents on a regular calculator that's not squared. I mean, I guess you could just use the calculator we've got, but sometimes when it doesn't have a square, you've got to do like a little up arrow and then put in whatever the number is. But I'm not finding a good calculator for that. So use the Desmos calculator. If you want, I'll even put the link for it in your Google Classroom so that you have access to that. What did we learn using that calculator just now? We learned that if we did 6, right, we had our base of 6, and we hit that A to the B because it wasn't 2. When we just put 5 in, it's going to give us our solution, right? Which we can put in as 7,776. Let me get away from this thing right here. So let's look at this one. What would we have with 23? Well, 23 times 23, our base is going to be 23. How many times are we multiplying it? 2. So it's 23 to the second power. What does that equal? I don't know. Like I can't multiply that in my head, 23 times 23. But we can come over here to this calculator and we can go, okay, we've got 23. And here it just gives me A to the 2. But if it's anything else, I could just put the B and put in whatever number it is. And we're going to get 529. So not too hard, right? Notice this one though. See how it says -3 times -3 times -3 times -3? When we raise this to a power, notice they're all in parentheses because it reminds us that we also have to multiply that negative each time. And that's really important because if we don't, it could change our solution. How many times am I doing it? 4, right? So it's going to be -3 to the 4th power. And I'm just going to tell you right now that's going to equal positive 81. Even though we're multiplying -3, negative times a negative equals a positive. And then when we multiply that times a negative, we get a negative. And then when we multiply that times a negative, we get a positive, right? And so that's why we get a positive 81 out of it. And that's why it's really important to include that negative when we square it in the parentheses or when we 4th power it, right? Because we need to understand that we're multiplying -3 times -3. Well, -3 times -3 is 9, right? Well, 9 times -3 is -27. And -27 times -3 is positive 81. And that's basically what we're doing when we do problems like this, right? Is we're just multiplying it multiple times. Here we have 11 to the 3rd power, right? And I can plug that into the calculator. You don't have to know that off the top of your head. And you'll get 1,331. Here we've got what? -4 to the 1, 2, 3, fourth power. And that's like saying -4 times -4 times -4 times -4. And I know I'm going to get a positive number, and it's going to be 256. Now, use the calculator. I will put the link in the, you already have a link in there? I know, I'm not using the calculator anymore. But I'm going to put the link to that Desmos calculator in your Google Classroom so that you have access to it. So it's one that you've seen me use. How am I going to write number 6? How am I going to write that as an exponent? Allison, no, the 81 isn't negative, right? Because negative times negative is a positive. And then when we multiply the third negative, it becomes negative. But then when we multiply it times another negative, it becomes positive again. It's kind of easy to tell if you think about any time if I have like an even number of negatives, right? So if it's to the fourth power, it's going to be positive. If it's to the third power, it would wind up being negative, right? Or if it was to the fifth power, because every other one becomes negative. Like this becomes positive. This would be negative, but then when we multiply it times this, it becomes positive again. I know it's crazy. Choose your calculator, right? And make sure when you plug it into your calculator, like if, see, we have the -4s here. If I put it into the calculator, yes, Gabriel? Yes. Well, okay, let's look at it on the calculator, right? If I have 3 times 3, right? That's going to give me 9. If I multiply it times another 3, that's going to give me 27. If I multiply it times another 3, that's going to give me 81. And I know that we had -3s, right? That was -3 times -3 times -3. So let's look at it that way. If I have, I'd have to put it in parentheses. So I'd have to go -3 times -3, right? Again, that's giving me +9 because a negative times a negative is a positive, right? Well, what if I multiply it times another -3? Whoops, I should probably put the 3 in there. And now notice it's -27 because we just multiplied a positive times a negative. But then when we go to multiply the other one, because we were doing it 4 times, it's to the fourth power, right? So when we go to multiply this next -3, it's going to become positive 81, right? And that's all we did with this, but we could have saved ourselves all this time, right? Just by raising it to the fourth power, right? So if we look at, what did we just do? What was the last one we did? -4 to the fourth power. That's how we got a positive 256, right? Because we did it 4 times. So -4 times -4 is positive 16 times -4 is, I think, gosh, I don't know. I think it's -64. And then -64 times -4 is positive 256. So make sure that when you put your negatives in there, that you put them in parentheses so that you're squaring that negative too. So here, what do we have? We have 2 is our base, and we're raising it to the 1, 2, 3, 4, 5, 6, 7th power, right? And if we plug that into the calculator, we're just going to put it in as 2, and we're going to hit this A with the little b above it, and we're going to put in 7, and it's going to give us 128. What about when we have a fraction? Ooh, how's that going to work? Well, here I have 4/9 times 4/9. So that would be 4/9 squared, which means that we square each part of that. So we would have 4 squared, which is 16, over 9 squared, which is 81. So you're going to square the 4 and you're going to square the 9, right? You're going to raise each piece to that power. So here where I have 1/3 to the 4th, right? That's like saying 1 to the 4th, oops, sorry, to the 4th, over 3 to the 4th. And why is that important? Because when I rewrite this as a value, 1 to the 4th is still just 1. 3 to the 4th is 81, right? So it's like you're solving two problems in one. -10, that's just squared, right? That's -10 to the 2nd power, which is just 100. What do we have over here though with these A's? We have we got 1, 2, 3, 4, 5, 6, 7 A's. That is just A to the 7th. And when we do the value of that, we don't know what A equals, right? We have no idea. So that's still just A to the 7th because we don't know what that equals, right? Here I have 1 over X. How many times do I have it? How many times do I have that 1 over X? 4. So we're going to raise it to the 4th power, right? And so that's going to give me 1 over X to the 4th. I could write it as 1 to the 4th over X to the 4th, but what is 1 times 1 times 1 times 1? All right, still just 1. Yeah. This one, as we move down, look at this. We have M's and N's. How many M's do we have? How many M's do I have? 2. I saw that, Caitlin. How many N's do I have? 3. So I can't bring these together. This is just M squared N to the 3rd. This one, they mix it up, but everything's multiplied. I have R's and I have P's, right? I have 1, 2, 3, 4, 5, 6 R's, right? So we'll go R to the 6th, and we'll have P to the 3rd because there's 3 of them, right? That's all I have to do. C's, I've got 1, 2, 3, 4 C's, C to the 4th, and I have 1, 2, 3, 4, 5 D's, so we get D to the 5th. What do these look like over here? Same. R to the 6th, P to the 3rd. Because I don't have any number values for them, so they're just going to stay like that. Does that make some sense? So it's kind of easier when you don't have a number value, right? Because everything just stays the same. We're going to move on now. We're going to talk about, all right, tell me when you're done. Got it? Okay. It'll I'll leave it up. Don't worry. I'll leave it up. It's okay. You need me to go down like this, Allison? Okay, I got you. I'll give it a few minutes. It's gonna make for a boring video. Done? Are you done too, Allison? Are you good? Everybody good? I'll leave like the bottom ones visible. So we're talking now about perfect squares. The square of an integer is called a perfect square, right? Perfect square, right? And that's when we're talking about, okay, if I have a bug that keeps flying in front of my face. I'm not being weird. 1 squared, that's just 1 times 1, and we get 1. 2 times 2, 2 squared is just 2 times 2, and 2 times 2 is 4. 3 squared is 3 times 3, we get 9. 4 squared just means 4 times 4, and we get 16. 5 squared is just 5 times 5, right? And we get 25. 6 squared, 6 times 6, we have 36. Why am I doing all of these? Because it's going to come in handy. That's why I'm doing it. 7 times 7 is 49. So 7 squared is 49. 8 squared is 8 times 8, which is 64. 9 squared, 9 times 9, 81. 10 squared, 10 times 10, 100. The opposite of squaring a number is finding the square root, right? What it means to find the square root is we're talking about, well, what number am I multiplying by itself to get that square root? And we keep it under what we call a radical sign. That's this little thing. It almost looks like a division, but you've got that little piece that's up there. The radical sign says that we're looking for the square root of x or whatever's underneath there. So if I have the square root of 4, I'm saying, well, what number times itself equals 4? And we know, like up here, well, it's 2, right? So we could go, oh, it's 2. What number, if I have the square root of 9, well, what number times itself equals 9? And we know that that's 3, right? And that's what we're looking for with these. Here it's saying circle each value that is a perfect square. Well, we went through and did some perfect squares, right? So which ones are these? Well, we know 16 is because we can see it up here, right? Perfect square, 4 times 4 equals 16, so we know that's a perfect square. 20, though, look up here. Are any of these 20? No, right? We know that the only thing between 16 and 36 is 25, right? We know if we square 4, we get 16, and if we square 5, we get 25, and 20 is somewhere in between that, so it's not a perfect square. What about 441? Well, here's what I know. I know that 20 squared is 400, and I don't know what 21 squared is, but how am I going to find out? Well, let's look at 21 times 21, right? Look at that. What did we get? Exactly what we were looking for. So we know that this Perfect square, right? It's 21 squared. Is 81 a perfect square? Yeah, it's 9 times 9. What about 225? I saw Gabriel shake his head. Did you shake your head? Is 225 a perfect square? Let's ask Isabel Lopez. Isabel, is 225 a perfect square? Okay, that's what I thought. Bailey. Bailey, is 225 a perfect square? All right. Bailey's not here either. How about Lily? Is 225 a perfect square? Well, might be. Might be. I think it might be. Daniel, what do you think? 225. Perfect square? I don't know. I don't know. I'm calling on, notice I'm calling on all the people who don't have their cameras on. Because if they don't answer, I'm calling their parents, right? So luckily you guys answered. I think that it is a perfect square. What do we know? What's the last perfect square that we know? We know that 10 squared is 100. And we know, didn't we just find out that 11 squared or something like that? What did we find out recently? We know that 21 squared is 441. So we know if it is a perfect square, it's got to be between 100, right? So 10 and 21. It's in a 5 number, so it should probably have a 5 in it, right? If it's going to end in 5. So let's look at 15 squared, 225, right? Start thinking about the things that you know are around it, right? We knew that, what did we know? We knew the biggest one we knew was 100, right? 10 squared is 100. So we could start looking at things over 10, right? And squaring them. We could have gone, okay, well, is it 11 squared? Is it 12 squared? Yes, Leah. Okay. That's an irrelevant question for right now, Leah. We're in the middle of a lesson. A perfect square is the square of an integer. So any whole number that's squared is a perfect square. So any whole number times itself. Like 1 squared is 1, 2 squared is 4, 3 squared is 9. So we're looking for things that are like a whole number. Like 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 16 is a perfect square because we know that 4 times 4 equals 16. 441 was a perfect square because we learned that 21 times 21 is 441. 81 is perfect square because 9 times 9 equals 81. You're welcome. So 290, is that a perfect square? I don't even know the answer to that. Did somebody try it? So what do we know? 16 squared is 256, right? And we know 290 is bigger than that, so let's look at 17. 17 squared is 289, which means 18 squared is going to be way higher. So whoever said no is absolutely right. What about 25? So we know that's good. What about 500? Well, it would have to be more than 21, right? Because 441 was 21. So let's look at 22 squared. Nope. What about 23 squared? Oh, that's like the square right there. 23 squared, 529. So no, right? Because we checked 22 and it was less than 500, and we checked 23 and it's more than 500. So there's no way that 500 can be a perfect square. What about 900 though? Well, I'm thinking that 9 is a perfect square, so it's 3 times 3, so maybe 900 would be 30 squared. So that's kind of what made me think of it, is that 9 is a perfect square, so maybe 900 is too. And it is, it's 30 squared. So when we're looking for the square roots, we're looking for numbers that are like this, these perfect squares underneath that little symbol that we call the radical, right? And we know that 4 is a perfect square, right? Because 2 times 2 equals 4. So the square root of 4 is 2, right? 361, is that a perfect square? I don't know. What would it be? Let's go 361. Let's try. We know 15 is 225, so let's try 18 squared. No, still bigger than that, right? What were we looking for? 361, so let's try 19 squared. 361. So that's how you're going to have to play with it a little bit, right? You're going to have to look at numbers. It says that these each have a square root, so we know that something's going to work, right? It's just a matter of finding out which something. I know I ran long today because that was the bell. You're not having to do any problems like this where you're looking for the nearest tenth on your assignment. So you're only going to have to do these kind of problems, where you have to find like what's the thing that makes it work, right? What's your square root? You know there's going to be something, right? Use your calculator and Desmos to find it. I'm going to let you guys go because you got another class after this one, as do I. I have to go teach my other class in another room. I'll get the notes posted and I will get the video posted.